Texan Global School. Operations with radical expressions. In this class, the processes of solving operations with radical expressions are analyzed. Recall that the nth root of a real number is denoted as the nth root of a, which is equivalent to a raised to the power of 1 over n. The index is the n and the a is the radicand. We will be using the laws of exponents and radicals to solve the operations. Now, a perfect root is one in which the value of a radical is a rational number. For example, the square root of 4 equals 2, since 2 times 2 is 4. The cube root of 27 is 3, since 3 times 3 times 3 is 27. The square root of 3 to the 8th power simplifies, using laws of radicals, as 3 to the 4th power, which is equal to 81. Finally, the fifth root of 32 can be represented as the fifth root of 2 to the 5th power. So, using the laws of radicals, we have the fifth root of 2 to the 5th, which is equal to 2. We can see that all the results of the radicals are rational numbers. On the other hand, a root that is not perfect is one in which the value of a radical is an irrational number. For example, square root of 2, cube root of 2, square root of 3, square root of 5, etc. All these radicals belong to the set of irrational numbers, since they cannot be represented in the form p over q. Gaubrun states that the standard form of radical expression is one that has a positive radicand and an index of the radical reduced to its lowest expression. Also, the one in which the exponent of each factor of the radicand is a natural number less than the index of the radical. There must be no fractions in the radicand and no radicals in the denominator of any fraction. Let's see an example. We will obtain the standard form of the following radicals. We must separate factors from the radicand so that we can calculate the roots of one or more factors. In the square root of 20, the radicand can be separated into factors 4 and 5. In this way, applying the law of radicals, we have the square root of each factor. So, the root of 4 is 2 since it is a perfect root. However, the square root of 5 remains the same since it is not a perfect root. Thus, 2 times the square root of 5 is the standard form of the square root of 20. Now, at the square root of 63, we can separate the radicand as 9 times 7. Applying roots to each factor gives us the standard form of 3 times the square root of 7. Finally, at the square root of 363, we can factor the radicand as 121 times 3. Square rooting each factor gives us 11 times the square root of 3. In this other example, we will first transform 64 as 2 to the 6th power. We apply radical laws with the same index to each factor and simplify exponents, obtaining thus 2t squared by the cube root of w. As can be seen, the expression meets the characteristics of the standard form of radicals. In this example, we cannot get the square root of 8 since 8 equals 2 cubed. It is not a perfect root. So we will decompose the 8 into 2 squared by 2 in order to get the standard form. X to the 4th remains the same since the exponents can be simplified. Cubic y will be broken down as y squared times y. We group the factors with even exponents that can be simplified and those that can no longer be simplified, such as the 2y. We apply the laws of radicals to each factor, obtaining 2x squared y times the square root of 2y. In this way, the exponent of each factor of the radicand is a natural number less than the index of the radical. Two or more radicals are similar if they have the same index and the same radicand. This implies that they can be added or subtracted in order to simplify. To simplify and combine an expression with radical expressions, we must transform each term into its standard form and add or subtract similar radical expressions. Let's see an example. We will simplify and combine the following expression. First, we transform each term into its standard form. The standard form of the square root of 45 is 3 times the square root of 5. The square root of 32 is 4 times the square root of 2. The square root of 20 is 2 times the square root of 5. And the square root of 50 is 5 times the square root of 2. Now, we identify similar radical expressions. The radical must be exactly the same to be similar. Only the numerical coefficient can change. So 3 times the square root of 5 is similar with 2 times the square root of 5. And negative 4 times the square root of 2 is similar with negative 5 times the square root of 2. We group them together and apply distributive law to be able to add them. We simplify, resulting negative 9 times the square root of 2 plus 5 times the square root of 5, already sorted. In the following example, we already have the terms in their standard form. So we identify similar radical expressions. It is suggested to use colors to be able to identify them easily. We group together similar radical expressions, and applying the distributive law, we simplify, thus obtaining 2 times the square root of x plus 12 times the cube root of y. The product between two radical expressions with the same index is made by multiplying the radicands and indicating the product within the root with the same index. For a quotient between two expressions with the same radical, it is similar. The radicands are divided, and the result remains within the same radical. In this example, we will multiply the square root of 12 by the square root of 45. To make the process easier, it is suggested to convert each factor to the standard form. The square root of 12 is 2 times the square root of 3, and the square root of 45 is 3 times the square root of 5. We then perform the product of 2 times 3, and since both radicals have the same index, we can multiply radicals, resulting 6 times the square root of 15. In this next example, we will still transform both the numerator and denominator to standard form. The square root of 12 is 2 times the square root of 3, and the square root of 27 is 3 times the square root of 3. We can directly cancel identical factors, remembering that a number divided by itself is 1. Or we justify using laws of radicals, where, since the divided radicals have the same index, the radicands are divided, and the result remains within the same radical. The radicand simplifies to 1, resulting in 2/3. The laws of exponents, laws of radicals, and the distributive law of multiplication are used to make a product or quotient between an expression of one term with another of 2 or more terms. Essentially, the distributive law applies. Then, each term is simplified as in the previous case independently. If similar radicals exist, they simplify at the end. In this example, we can see that, applying the distributive law, we will multiply the square root of 3 by each of the terms of the expression. We separate factors in each of the terms to perform the products and simplify. In this next example, we first transform each term in the numerator and denominator to its standard form. Later, when applying the distributive law, we divide each term of the expression of the numerator by the denominator. Next, we apply the laws of radicals to simplify each term. We can see that equal factors cancel, understanding that the same quantity divided by itself is 1. We will use the arithmetic algorithm to perform multiplications between expressions with more than 2 terms. We must consider the ascending order of the radical expressions. Arrange the terms in 2 rows called multiplicand and multiplier. Then multiply each term of the multiplier by each term of the multiplicand. Arrange each product according to the corresponding column so that the addition is facilitated. And finally, add similar radicals. When performing the multiplication in the following example, we write the multiplicand and multiplier first. Next, we multiply the last term of the multiplier by each term of the multiplicand. Now we multiply the next term of the multiplier by each term of the multiplicand. We add radicals and similar radical expressions, thus obtaining 5 minus 2 times the square root of 6. This example can also be solved using special products. In this case, square of a binomial, since the same expression is being multiplied by itself. Then, we locate the values of a and b to substitute in the formula of the perfect square trinomial. As we can see, by simplifying using laws of radicals, results the same. Finally, we can have special transformations to simple radicals, as shown on the board. We can see that there must be a relationship between the value of s and the value of p. So, the square root of s plus or minus 2 times the square root of p equals the square root of x plus or minus the square root of y, if and only if S equals x plus y, and p equals x times y. Let's see an example. As we can see, the problem has the form discussed. We can find the relationship where s equals 4 plus 3, and p is the same with 4 times 3. However, we must adapt the radical since it is doubled as the one indicated in the formula. With this in mind, we substitute the values of x and y in the simple form, resulting square root of 4, which is 2, plus the square root of 3. Texan Global School. Global online learning. Knowledge for the world. www.texanglobalschool.com